I'm very happy to be here, and I'm a PhD student from KAIST, and actually my talk contains very basic concept for local and Tracy-Widom limits, so it may be easy for you. And my topic is the local law and Tracy-Widom limit for sparse stochastic flow models, and this is the joint work with Yang and Jun Lee and KAIST. So I start with the generalized beginner matrix. Generalized beginner matrix is n by n real symmetric random matrix whose entries are independent of the symmetric constraint and satisfy mean zero and variances of order 1 over n. And the sum of variances in each row equals to 1. Also, for simplicity, we assume the sub-exponential decay of the matrix entries like this. And if all of the variances are 1 over n, then we cover the standard beginner matrix. So I'm really interested in a stochastic flow model like this, and this is a network of American colleague football teams. As you can see, it has some community structures, and there are many edges within the communities and less edges between the communities. So this stochastic flow model can be defined by this. It is n by n symmetric matrix with k-square blocks of same size, and the blocks are based on the partition of the vertex set, and their size are same. And we may consider two types of the edge probability depending on whether I and j are within the same vertex set or not. So this is the adjacency matrix of the stochastic flow model, and this is n by n matrix with k-square blocks of size m, and the inter-community probability is p, and the intra-community probability is q. And this figure is the heat map of stochastic flow model with 1,000 vertices and 5 clusters, and inter-community probability is 0.3, and intra-community probability is 0.13. So bright means there are many edges. So for this generalized beginner matrix, the empirical spectral distribution converges weakly to the semicircle distribution law SC, and this is called beginner semicircle law. And this is the plot of eigenvalue distribution of GOE against the red line is the semicircle law. So this semicircle law is given by this equation, and for a probability measure, we define its Stieltjes transform by this, and then we can compute the Stieltjes transform of the beginner semicircle law by, and it's explicitly given by this. From this, we can show that it follows the 1 plus en plus m squared equals to 0. And one of the important properties of the Tracy-Widom beginner matrix is some edge universality, and the shifted and rescaled last eigenvalue of the beginner matrices follows the Tracy-Widom distribution, which is a cumulative distribution function that satisfies this equation. And I plot the histogram of the largest eigenvalue of the beginner matrix against the Tracy-Widom distribution. This blue line is the Tracy-Widom. And the similar result holds for the generalized beginner matrices. The shifted and rescaled largest eigenvalue of the generalized beginner matrices also follow the Tracy-Widom law. And to control these things, we define the green function by inverse of h minus ci, and by definition of it, I plus cg also equals to h times g. And we define the normalized trace of g by 1 over n times trace of g. And then the Stieltjes transform of empirical eigenvalue distribution is equals to the normalized trace of g. And this is the spectral domain for my main result. There are many results and applications for the stochastic flow model, but the real world case is very sparse. For example, from the Facebook user statistic in 2017, there are 2.01 billion users, and the average number of friends is 155. And for given Erudit Renyi graph G and P, in here we have the average degree 155, and for when n equals 2.01 billion, this average number of n is between log n and n to the 1 over 3. So we can say that this probability p is between log n over n and n to the minus 2 over 3. So p is very small, and this sparsity must be considered when the average degree is much less than n. And now I will talk about my main results. So this is the model for my main result, which is the balanced generalized sparse random matrix with sparsity q. But this name is too long, so I will call it by sparse SVM. So sparse SVM is n by n real symmetric random matrices with k balanced communities which are same size and satisfy these moment conditions. So it's mean zero sparse. If we extract some mean metrics from previous stochastic flow model, and their entries are satisfied, when their entries satisfy this moment condition, then it will be a sparse SVM. So we assume, in here we also assume that the normalized condition that the sum of variances in each row equals to 1. And there are two types of probability distribution, inter-community probability and intra-community probability distribution. So compared with Wigner matrices, the variances are not identical with block structure, and the matrix is very sparse. So if Q is proportional to n to the 1 over 2, it will be a Wigner matrix. And for the normalized adjacency matrices of Erdős-Renyi graph, we have Q squared equals to NP, which is the expected degree. And for the normalized stochastic flow model with K communities, we have also Q squared equals to the expected degree. So now I will introduce cumulants, something like moments. The logarithm of the moment generating function is the cumulant generating function. So if we differentiate it at k times and compute the value at 0, we can get the k cumulant. So for our model, that there is two kind of H probability. So we can abbreviate kappa ij as kappa s if I and j are within the same community, and kappa d for otherwise. So under the previous moment condition, kappa 1 is 0 and kappa k is bounded by this. And we also use the normalized cumulants by setting like this. So this is my first result. And there is an algebraic function m tilde, which is the still test transform of a deterministic probability measure, and this m tilde is satisfying this equation. And if there's no first term, then it will be a semicircle distribution, but there is term. And also the normalized trace of the green function satisfy this local law. In here, this is a random trace, and this is a deterministic one, and the difference of these two are bounded by 1 over q squared plus 1 over n alpha. So we proved that if m tilde let m tilde be a solution to this equation, and then we find the rho tilde, the still test inversion of m tilde. And we proved the properties of m tilde and rho tilde, including the location of the edge, and the regularity, especially the square root decay at the edge, and the stability. And this is my second result for the Tracy-Widom limit. And if H is a sparse SVM with sparsity Q is greater than n to the 1 over 6, then the shifted and rescaled loss eigenvalue of H converges to the Tracy-Widom distribution. So here we subtract L, not 2. And this condition is critical, I think. So if we subtract 2, then we will get the shifted Tracy-Widom distribution like this. And if we subtract L, then we, as you can see, you get the Tracy-Widom limit. So To prove the local law for sparse SVM, we did a prior bound, but in here we do not need any assumption about the block structure. So we can prove the weak local law for this generalized sparse random matrix. So there is no block structure, but there is sparsity condition and the normalized condition that sum of the variances in each row equals to 1. So follow the classical stretch based on Schur continuous formula and the self-consistent equations, we can prove this weak local law. So we can bound the off-diagonal term of G, green function, and the diagonal term of green function, and the normalized trace of green function. So these two bounds are optimal, but this is not optimal as you've seen before. This is optimal when this becomes 1 over q squared plus 1 over n eta. And now I will introduce about my proof. So if we define the polynomial P1, P2, and P by this, P1 is the solution for n tilde, equation for n tilde, and P2 is just a quadratic equation. In here, A is constant depending on H. And for the local law, we use the recursive moment estimate, which is estimate expectation of 2d power of P by 2d minus k power of P to show that P is very small using Markov inequality. To do this, I will introduce cumulative expansion, which is generalized Stein's lemma. So Stein's lemma is for centered Gaussian random variable. This holds, we can prove this by using integration by parts. And it can be generalized to non-Gaussian random variables. So if if y is centered random variable with finite moments, then this holds. We can compute the y expectation of y times fy by cumulus of y times the expectation of derivative of f. So I will introduce the basic case to how to use this cumulative expansion. So let W be a GOE, and we have the green function like this, inverse of W minus D, and from by definition, I plus DG equals to W times G, and in here, M is the normalized trace of G. So we can write expectation of 1 plus Dm like this, and by definition of G, I plus GG equals WG, so this is II entry of this one, so we can write this, and by matrix multiplication we can write this. So here G alpha I is the function of W alpha I, so we can use Stein's lemma here. So if we use Stein's lemma, then here we get some variance and the derivative of G. But this W is GOE, so we have this one is 1 over n, and we can compute this one like by this. So this term becomes m squared, and so therefore, if we can show that this one is very small, then expectation of 1 plus Cm plus m squared is very small. So using Stein's lemma for the Gaussian case, we get this bound. We can bound 2d power of 1 plus Cm plus m squared by this. In here, phi square is 1 over n eta, and by Young's inequality and higher order Markov inequality, we can show this. And MSC, which is the Stochastic transform of the same-step law, is the solution of this equation. So with Taylor expansion of M around MSC, we can conclude that this is bound M minus MSC can be bounded by phi square. The similar works for the sparse SVM. So we have P1, P2, and P, and we can prove the recursive moment estimate for P. So using generalized Stein's lemma, we can bound expectation of 2d power of P by like this. In here, psi square is 1 over q squared plus 1 over n eta. As before, just this term is changed by psi square. So by Young's inequality and higher order Markov inequality again, we can bound P by psi square. And since A is just a constant, so we can show that P2 is not very small. Therefore, this implies P1 is bounded by psi square, and M tilde is the solution for this equation. So if we use the Taylor expansion of M around M tilde, then we get the local law for sparse SVM. And for the Tracy-Widom limit, we use two methods. The first one is the isometric flow, which is the continuous interpolation between the sparse SVM and the generalized Wigner matrix. And the second one is green function comparison, which compares the edge statistics of H, which is the sparse SVM, with the edge statistic of the generalized Wigner along the isometric flow using green function. So the isometric flow looks like this. If t is 0, and it is a sparse SVM, and when t goes to infinity, it will become a generalized Wigner. So as it was proved that the local edge statistic of generalized Wigner matrix follows the Tracy-Widom. So along this flow, we track the change of the edge statistic between the sparse SVM and generalized Wigner using green function. So we use the green function in here. In here, M is the normalized trace of G, and MW is the normalized trace of GW. And with a good cutoff function, the distribution of the eigenvalues of the original matrix can be obtained by expectation of f of x. So using the isometric flow, one can show that expectation of f of x and expectation of f of xw, and their difference is very small. That implies the eigenvalue statistic for the original matrix, which is H0, the sparse SVM, and W, the generalized Wigner, is very similar. So you can prove by this, you can prove the Tracy-Widom limit by this. And this is the paper in arXiv. And thank you for your attention.
Questions?
The Tracy-Widom limit is true for p way bigger than n to the minus 2/3.
Yeah.
And do you expect like something similar than in Dershowitz where you transition to Gaussian fluctuation?
Yeah, if P is less than n to the minus 2/3, then it will be a Gaussian.
Yeah.
But there is low bound, but I cannot remember what is the low bound for Gaussian. If
It's
P,
minus set 7/9, I think.
yeah, right, maybe.
Okay, so you expect the same transition as Dershowitz?
Yes.
About the sparsity Q, I mean, do you think this is optimal, this n to the 6, or?
Which
not
one?
very good?
Ah,
The condition for Tracy-Widom mistake.
yes, this one.
Yes.
Yes. For proof for Tracy-Widom, yes, this condition is critical. If Q is less than n to the 1/6, and then we cannot find Tracy-Widom there.
But, I mean, this is because of your proof, or do you think you get something else?
Because of my proof,
Yeah.
in my proof.
So you expect this will hold for much smaller Q?
I don't think so. Because if Q is less than 1/6, then maybe it will be a not Tracy-Widom but normal distribution.
Yes, the question related to my first one, but here you say Q greater or equal than n to the 1/6.
Yeah.
But in the Dershowitz, when you are exactly at minus 2/3, you get the combination of like Tracy-Widom and Gaussian, right?
Yeah.
So here, even at n/1/6, you get Tracy-Widom? Or is it strictly greater than n to the 1/6?
My proof works for when equal. When Q
Okay,
equals
so
to n
you
to
still
1.
get Tracy-Widom.
Any more question?
Well, thank you.